Our planet has this absolutely epic story to tell. A story of shifting continents, of mountains rising and falling, and of life evolving in the most incredible ways. But this story isn't written down in books, it's written in stone, in the very layers of the earth right under our feet. So how in the world do we actually read it? So, that's the big question, isn't it? We're talking about a history that goes back 4.6 billion years. I mean, how do you even start to decipher a book that old? A book where the pages are literally made of rock and the chapters are buried miles deep. It's kind of like being a detective, trying to piece together the oldest story imaginable. Well, the very first step is you have to learn the language. And in geology, the fundamental grammar, the basic rules of how this whole rock book is put together, is called stratigraphy. This is the foundation for absolutely everything else. At its heart, stratigraphy is just the study of layered rocks, which scientists call strata. It's all about trying to figure out the relationships between these different layers. Which one came first? How do they connect to each other over long distances? Basically, it's the science of putting all the pages in the right order. And the single most important rule here is so simple, it's brilliant. It's called the law of superposition, and it was figured out by Nicholas Steno way back in 1669. The idea is just this. In a stack of rocks that hasn't been disturbed, the oldest stuff is on the bottom and the youngest stuff is on top. It seems like total common sense now, but this was the revolutionary idea that first let us turn a chaotic mess of rocks into a readable timeline. Okay, but it's not just about what's on top. Steno gave us a few other key principles to fill in the details. For example, original horizontality means that sediments usually settle in flat layers. So if you see rocks that are all tilted and bent, you know something big must have happened to them after they were laid down. And the cross-cutting relationship is another fantastic tool. If a crack or a fault line cuts through a bunch of rock layers, that crack has to be younger than the rocks it's cutting through. It's just geological logic. All right, so stratigraphy gives us the order of the pages, but how do we know which chapter we're reading? How can we tell if we're in the age of dinosaurs or way back in the age of the very first complex life? For that, we need bookmarks. And lucky for us, nature provides them in the form of fossils. And that's where paleontology comes in. It's the study of all this ancient life. And look, it's not just about digging up awesome dinosaur skeletons, right? It's about understanding the entire history of life on our planet, from tiny little microbes to giant mammoths, and using their remains to paint a picture of the world they lived in. This chart really gets to the heart of one of the most powerful ideas in all of geology, what's called the principle of faunal succession. It just means that life evolves in a specific, predictable order over time. So if you find a very particular type of fossil, say a certain trilobite, you know exactly which chapter of Earth's history you're looking at. No matter where you are on the planet, these fossils are our ultimate timeline. And this is where it all clicks together. See, fossils aren't just these cool little things stuck in the rocks. They're actually the key to understanding those rock layers. They're what allow geologists to look at a layer of rock in North America and confidently say, hey, this is the exact same age as this other layer of rock over in Europe, just because they have the same unique set of fossils. It's an incredible tool. Okay, so we've got the page order and we've got our fossil bookmarks to tell us which chapter we're in. But where in the world are we reading this story? To actually place our story onto a map, we need a third crucial discipline: surveying. Well, that's what surveying is all about. It's the science of measurement. It's how we figure out the precise position, the distance between 2 points, and the elevation of any feature on the Earth's surface. It's all about building a super precise framework, like a map grid, for the whole geological story. And believe me, we've come a long way from the old days of just using chains and compasses. Modern tools like this total station you see here, or GPS and satellite technology, allow for mapping with unbelievable precision. And this kind of tech isn't just a nice to have. For a geologist out in the field, it's an absolute game changer. Yeah, the best way to think about it is that surveying gives you the ground truth. It gives geologists the exact coordinates and elevation for that cliff face, that fault line, or that fossil bed they're studying. Without it, a geologic map is basically just a rough sketch. It's the surveying that turns it into a real, accurate scientific document. All right, so we've got these three totally distinct but super powerful fields: stratigraphy, paleontology, and surveying. Each one is its own specialty for sure, but the real magic, the real breakthroughs, happen when they all come together to work towards one big goal. And what is that goal? It's to create an accurate geological map. And we're not talking about just a pretty picture for the wall. A geologic map is a deeply detailed historical document. It tells us what rocks are where, how old they are, and how they're all put together. It's like the final published edition of Earth's story for that one particular area. And this table just breaks down the team effort perfectly. To make one of these maps, you've got to answer three fundamental questions. Surveying nails the where is it question. It gives us the precise location. Stratigraphy handles the what is it question. It tells us what the layers are and how they're stacked. And finally, paleontology comes in and answers when is it from by giving us the age from those amazing fossil bookmarks. Each one is a critical piece of the puzzle. So at the end of the day, it's that incredible combination that turns what would otherwise look like a meaningless jumble of rocks into a coherent, detailed, and completely readable history of our planet. It's just a beautiful example of how different sciences have to work together. So we've really just scratched the surface of how scientists read the Earth's history, looking at the big picture of how these fields connect. But honestly, each one of these topics is a whole universe you could get lost in. And that brings us to you. Now that you've seen the overview, what part of this whole story really grabs you? Do you want a deep dive on the weird and wonderful creatures from the Cambrian explosion? Or maybe an explainer on how radiometric dating gives us those super precise ages for rocks? Or how satellite imagery is changing everything for modern surveyors? Let us know in the comments below. We're excited to see what you want to explore next.